Okay, so we'll continue with the second lecture of Gregorio. We will talk about polymers and Pontifica.
Thank you. Okay, so this is a joint work with Francisco Metz. And Alejandro Ramirez. So now, so we consider a second type of mean field model for directed polymers. So this will be polymers on the complete graph. So time goes in this direction. Time is discrete. And at each time you have a copy of Gn, the complete graph on with n sides. So a path here is just, it starts somewhere and then just picks up whatever site on the graph. So it could start here, go there, and of course it doesn't have to go to the nearest neighborhood. It can go here and maybe go back over there. So that's the set of paths. So now the environment is the following. So say that this is instant s minus 1. This is instant s. These are sites I and j. So to each bond, we will attach a random variable omega, which will be indexed by the two extremes and time. So this will be a collection of IID random variables. And the weight of a path will just be the product of these random variables along the trajectory. So you have to think that now the omega is playing the role of the exponential of beta omega we saw last time. So let's say exponential of beta eta. So we have a bit of a change in the notation. So let me fix notation. So the paths will be denoted by J. So G0, G1, G2, etc., where GS belongs to the complete graph with n sides. The environment will be given by this IID collection of random variables. And as I said, the weight of a path Wt of j is the product of the omegas along the path. So at each instance, the path jumps from its position at time s minus 1 to its position of at time s. So this is the I in this picture, and that would be the j. And then we write a partition function, a point-to-point partition function over all paths that go from site I at time 0 to site j at time t. This is just the sum of the weights over all such paths.
The weights are positive, right?
Thank you. Yes, the weights are positive. Yes, so these are IID positive. Okay, so that's the model. So let me start showing what the basic recursion for this model is. So what we will do, we will decompose the paths according to its positions at the position right before the end, so at the position t minus 1. So let's say this will be a site L. So decompose according to the value of L. So L can take any value on the complete graph. L runs from 1 to n. So going from time 0 to time t minus 1, you pick up a piece of partition function over all paths that go from I at time 0 to L at time t minus 1. And then you have to multiply by what is left, which is just the weight from site L to site J at time t. So the interesting thing here is that this looks like it's a matrix-like product. So if you iterate this relation, you get that this is exactly the entrance of a matrix. It's the ij entry of a matrix where this pi t is a product of matrix X and XS is just a matrix whose entries are the omegas at time S. So basically, there is a complete analogy between this model and products of product of random matrices with positive entries. So we had several motivations for studying this model. So the first one is that again it's a simplification. So it's a model where you can expect to be able to say very precise things. And it's quite natural. This would be the analog of the Curie-Weiss model for the Ising model, for instance. And as I said, the nice simplification is that we have a link with products of random matrices, which is a well-known field. Yes?
If you look at the spectral distribution of this matrix, it gives you something interesting related to the partition function?
Spectral distribution, I don't know, but actually we will be interested in the Lyapunov exponents. Okay, so second motivation is that it's you could also write down the last passage percolation model in the same setting, and that's something that had been done by Brunet and Derrida, and their motivation was to study some kind of population, mean field population models with selection related to the KPP equation. So it's a positive temperature. Version of a last passage percolation model introduced by Brunet and Derrida. And the third motivation is that there is a solvable model. So this means that there is a special distribution on the environment for which you can make very precise computations. Okay, so the plan is the following. I will first discuss the general properties of the model with general environments. So we will talk about the free energy. Then we will go to the solvable model, so I will show you what you can say in that case. And at the end, I will talk about perturbative results, so we are able to get some conclusions when we start with a distribution which is close to this solvable distribution. Okay, so the free energy is defined as usual. So now remember that n is fixed. N will be fixed for in this section, so n is the size of the system. So the free energy, we will call it Vn. It's the limits now when t goes to infinity. T is the length of the polymer. 1 over t logarithm of Zn 0I dj. Yeah, so before that I would, yeah, so I will introduce a slightly more general setting. So yes, so this so we can take advantage of this relation with random matrices to write a slightly more general model. It's nothing. So you can think that instead of looking at a point-to-point partition function, you can look at a partition function with, say, a more general initial condition. So what we will really study is the following. So we will start with an initial vector Zn0 in R plus to the n, maybe without the 0, and then to go from the vector at time t to the vector at time t plus 1, we will just multiply by these matrices x. Okay, so for instance, the previous situation can be recovered as follows. So you take an initial vector which is just which has component I equal to 1 and all other components equal to 0. So this will give you the 0I here. And if you look at the jth entry of the partition function, it will give you exactly the point-to-point partition function. So let me rephrase the free energy in this setting. And we will see that we will lose actually track of the coordinates. So this will be a common value for all values of I from 1 to n. Okay, so this can be studied with the usual program, which consists of subadditivity plus concentration. But actually it will be a better idea to try to exploit the relation with random product of random matrices to get more precise information on this free energy. So I will start giving a very simple decomposition. So I will write the logarithm of the nti as the sum of the logarithm of something I will call xnti plus the one norm of this vector znt. So it's just the sum of the values of the coordinates of these vectors zn. So here xnti is just the renormalized partition function. So we just renormalize by the total mass. Okay, so that's nothing. So one interesting thing maybe about these objects is that it's actually a Markov chain. On the simplex. Okay, so it's not difficult to see that it's a Markov chain. It's just what you do. The update step is just to multiply by this random matrix, then you normalize, you project it on the simplex, and you do again the same procedures. Completely Markovian. But the simple observation here is that it lives on a compact space. So when you divide by t, this thing will just disappear. And you see right away that the free energy will not depend on the index I. So this is the way you can exploit the relation with random matrices. So there is a relation with the Perron-Frobenius eigenvalue. So you can prove that this quantity stays close to the logarithm of this Perron-Frobenius eigenvalue. So the supremum over all t bigger or equal to 1 So this difference stays uniformly bounded with t, where this lambda can be obtained by a variational formula as a minimum of a maximum and that's a well-known object, so it has been very extensively studied by the whole community of product of random matrices. So basically, we'll be borrowing results from papers of Agnew and Agnew Hervé, where the asymptotic of this object is studied. So this is reminiscent of the fact that the asymptotics of the entries of this matrix are all the same, and moreover they coincide with the asymptotics of the Lyapunov exponent. Sorry? Oh, pi t is the matrix.
X.
Yeah, it's the product of the concatenation of the X of the matrix which carries the disorder. Is it okay? It's.
You have the matrix X?
Yes, to go from one state to another, you multiply by the matrix.
Yeah.
So to go from the initial state to the final state, you just concatenate all these matrices xt, and pi t was just this concatenation.
Okay.
Okay. Okay, so we have basically a dictionary between this polymer measure and the products of random matrices, so we can take advantage of well-known results in that field. And what we obtain is the following theorem. So I have to make some assumption on the distribution of the environment. So we will assume that the log of omega ij at some moments. Then for all initial conditions, so first we have the existence of the free energy. So this exists. This exists P almost surely. And furthermore, we have fluctuations. And in this case, they will be Gaussian. So you center and renormalize the logarithm of the ntj. This converges to a normal random variable where sigma n is a strictly positive quantity. So all of this is, once you have this estimate, you just go to the random matrix literature and you collect the results you need. So maybe you comment on this sigma n being strictly positive. So that's a non-trivial fact, actually. In the field of products of random matrices, there are very precise geometric conditions on the matrix that ensure that this would be 0, for instance. And it's not difficult to see that these geometrical conditions are broken if you take IID matrices. So that's the general result. So maybe I should say a word about this problematic of weak disorder, strong disorder, both from the point of view of the free energy and from the point of view of this dichotomy of localization, delocalization. So first, from the point of view of the free energy, so I'm not even assuming exponential moments on log omega. So the annealed free energy might well be infinite. So in that case, you would have a finite free energy and an infinite annealed free energy. So trivially, you would be in a case of strong disorder. Now, of course, you could assume more on the law of omega, and again, write omega as exponential of beta eta, and try to play the same game we played on the tree. So we didn't play that game because we were interested in other questions. So my guess is that you can check pretty easily that you are always in a case of strong disorder. This should follow from some fractional moment computation, but again, I didn't check. So what's more interesting would be to talk about localization or delocalization of polymer measure. So of course, you could write down the polymer measure just as in the case of ZD or on the tree. But now you see we are on a finite state space, so maybe it doesn't really make sense to talk about delocalization, so the measure cannot really spread out. What you could do then is to take the size of the system to infinity and see what happens in that case. So this is what I can say. So the polymer measure, as you first fix the size of the system. You can show by compactness arguments that the polymer measure has a limit when t goes to infinity. So when the length of the measure, the length of the polymer goes to infinity. So we do have an infinite volume polymer measure. And actually, this polymer measure has an explicit stationary distribution. So what you could try to do is to take this stationary distribution and look at its behavior when the size of the system grows. So that we can do in the solvable case at least. And I won't talk much about this, but what we find out is that the stationary measure has some kind of Poisson statistic. And what we observe is that the size of the biggest atoms of the measure decays as a power of log n. So there is localization, but it's a rather weak notion of localization. So remember that for the model on ZD, the atoms are macroscopic. So the mass of the largest mass carried by the site is bounded away from 0. Okay? So here, the measure has atoms, but the atoms are rather weak. Okay, so that's for the general results. So let's go to the solvable model. So I have to tell you what the spatial law of the environment will be, and it's just a totally asymmetric stable law. With parameter alpha between 0 and 1. So I will call it S sub alpha. So first, this law has some properties. So the first one is that it lives on the positive real axis. So we are in the previous setting. So next, it is stable. So in the sense that if you take n independent copies of this law S alpha and you renormalize properly, so here you would have to divide by 1 over n to the power 1 over alpha. This has the same law as S sub alpha. Okay, so that's something you can verify directly. So a way to characterize this law is through its Laplace transform. So it has a very nice expression. So expected value of exponential of minus lambda as alpha is simply equal to e to the minus lambda to the alpha. This is for non-negative values of lambda. So for instance, you could directly check the second property from this exact expression. And the last property we will be interested in is about the tails of this random variable. So except from a few specific values of alpha, you don't have any explicit expression for the density of these random variables. But what you could say directly from Taubert theorems is that asymptotically the probability that S alpha is bigger than X decays like X to the alpha, and moreover there is an explicit constant which is gamma of 1 minus alpha. This is as X goes to infinity. So that's just by Taubert theorem. Okay. So let's make a very simple computation that will show us why this is so special for our model. So let's try to compute the law of the partition function with this environment. And for that, let's just try to compute its Laplace transform. So let's compute the expected value of the exponential of minus lambda Zn of t plus 1j. And we will condition with respect to the sigma algebra generated by the environment up to time t. So for that, just use the basic recursion we wrote before. So you decompose according to the step before the last step for the path. So you get a sum I runs from 1 to n for z and t, I, then the disorder from I to j at time t. This is conditioned with respect to ft. Now, once you condition with respect to ft, these are just numbers. So you can use the explicit expression for the Laplace transform. Then you use independence of this wij for different values of I, and what you end up with the exponential.
Should be wij of t plus 1?
You're right. Thank you. So this exponential of a sum just becomes a product of exponential. For each one of those, you compute the Laplace transform. So you get a lambda to the alpha, and then each one of these will carry a znti to the power alpha. And then you have to sum over I going from 1 to n. Okay? So you get that in fact, the partition function has almost a stable law. So you just get these things there. But you can get rid of these by just absorbing them in this lambda, which amounts to renormalize this by the alpha root of this value. So the conclusion is that the renormalized partition function, which I define as the n tj over the alpha norm of the n at time t plus 1. So the alpha norm is just the alpha root of this quantity. So when you compute the Laplace transform of this thing, this sum disappears. You end up with exponential of minus lambda to the alpha, and you get exactly stable alpha law. Okay?
This is conditioned?
Yeah, this is conditioned with respect to ft, but once you normalize the dependence on ft, somehow disappears. So it's an equality in law, say, for all possible realization of the environment up to time t. And moreover, they are independent. They are all independent of. I mean, if we take different t's, different j's, they are all independent. It's just a big sample of alpha stable random blocks. Okay. So that's the solvability.
J going from 1 to n, should that S thing shouldn't have alpha norm 1?
Oh, you are normalizing by the partition function at one time before. So these guys don't, the alpha power of these guys don't add up to 1. Okay?
You didn't prove independence, right?
No, I didn't prove independence, but it's the same. You can just take an array of these guys with different lambdas and everything will decouple. It's the same computation. Yeah, I didn't prove independence. Fine. Okay. Yeah, so I use the term alpha norm. Of course, it's not a norm because alpha is between 0 and 1, but just slight abuse. Okay, so let's update our decomposition based on this observation. So now I will write the log of the n tj as the log of this Sn tj minus something I will call phi n of t minus 1, where phi n of t is just the logarithm of this alpha norm. So again, I have a decomposition where I have a piece which is order 1 and something else. So this looks silly, but there is actually more structure into it. So this guy is special, and I will try to convince you why. So let's just write phi n t explicitly. So it's 1 over alpha logarithm of the sum. I runs from 1 up to n of the i's coordinate to the power alpha. So now what you could do is to renormalize by the alpha norm at time s minus 1. So what you get, so this is really nothing, I'm just dividing and multiplying by the same quantity. And then you have here 1 over alpha, the log of this, the log of this alpha norm, which is phi n at time t minus 1. Okay, so that's not very impressive. What is important here is that these two things are independent pieces. Okay? So this means that to obtain phi nt from phi nt minus 1, I just sum something which is independent. So this means that this phi n is a random walk. Okay? So I will denote the increment by upsilon t. So the conclusion is that phi n is a random walk with increments upsilon n, which are completely explicit. Okay? And that somehow justifies the... So why did I call the free energy Vn and not P as usual? Because now it's the same as before. So you have this decomposition of a piece which is order 1, and then something which will carry all the asymptotic behavior. So now Vn is just the speed of the walk. So it's just the expected value of this increment upsilon, and moreover, sigma square is just the variance of upsilon n.
Is this where you use alpha smaller than 1?
Well, if
Calculation left would also work.
yes, but I think that you will no longer have positive random variables. I mean, there is actually at the critical value alpha equal to 1, you get an asymmetric law, but it's not positive anymore. Yeah. Okay. So now that you have this, you can hope to get asymptotics of the free energy and the variance as the size of the system grows, because after all, this is just like an ugly combination of alpha stable laws. So the theorem is the following. So first we have the asymptotics of the velocity. So at first order you have a growth of log n, then you have log n. Next follows the logarithm of an explicit constant, then something which is small o of 1. And we also have the asymptotics of sigma square n. So this behaves like a constant over logarithm of n. Okay. So this is this kind of asymptotics is reminiscent of what happens in certain population models. So this is, as far as I know, known as Brunet-Derrida behavior. So that's more proper of models close to this KPP equation. Okay. And there is a very simple heuristic that gives you at least an idea of why you should have this asymptotics. So remember that this upsilon is 1 over alpha logarithm of a sum of alpha powers of independent S alpha random variables. Okay. Now, Si alpha has 1 over x tails. So it's in the domain of attraction. Of a totally asymmetric law with parameter 1. Okay. So actually you have a completely explicit convergence theorem that tells you how to go from these sums of random variables, so how to center them, renormalize them, and get this totally asymmetric law as a limit. And it's the following. So this converges in law to the aforementioned random variable. So now you see that if you renormalize properly what's inside the parenthesis, what you get is that this sum divided by n log n converges to, should converge in some way to this constant. Okay. So very nicely, you take the logarithm of this thing, and you get the log n, you get the log n, you even get the explicit constant. So that's just the heuristic, of course, to go from this convergence to convergence of the moments. You have to work a bit, but that can be done. And there is, well, the procedure for the variance is also pretty similar. Okay. So now let me talk about perturbative results. Okay. So this is what we can prove. So fix on alpha between 0 and 1. Take independent random variables that will not be stable laws, but almost. So they are IID with Laplace transform phi of u. Such that one minus phi of u behaves like u to the power alpha when u goes to 0. Okay? So that's something that is satisfied by this exact Laplace transform of the stable distribution. And in particular, it tells you something about the tails of W. So again, by Taubert theorem, this tells you that the tails of W decay as 1 over x to the alpha. Then, for all t bigger or equal to 2, and for all I between 1 and n, so we look at this renormalized partition function. So this is the quantity which was exactly distributed as a stable law in the stable case. So this converts in law to a S alpha random variable. So furthermore, you could also take a collection of this random variable with a fixed side, and you can show also that they converge to an independent array of alpha stable random variables.
So there's no small parameter or something?
No, that's true. You take something which is not too far away from the stable law, and you get stable law at the end. Okay? So let me give you some ideas of proof. So it's quite a simple idea. So this condition, you could rephrase it as in the following way. Is that the Laplace transform of your random variable omega, it's almost the Laplace transform of the stable law plus a small correction, where epsilon u goes to 0 as q decreases to 0. Okay? So let me call this thing z bar. And let us use our recursion once again. So z bar ti is sum over j running from 1 to n. Then I have the z at time t minus 1 position j divided by its own alpha norm times the disorder at time t. So this is something I will call A and j omega j I t. Okay. And now these guys are normalized by their own alpha norm. So these weights actually have sum of alpha powers equal to 1. So that's something we'll use. And now let's again perform the same computation for the Laplace transform of this object. So again, condition on ft minus 1 this time. So by the same argument as before, what we end up with is a product, j goes to 1 to n, of the Laplace transform, but now evaluated at u times a and j. Okay. Now use this expression there. Put everything back together, so what you get is exponential minus sum j runs from 1 to n of u, a, and j to the power alpha. Then comes the 1 plus epsilon of u, a, and j. Okay? So now just use the fact that this a and j to the alpha add up to 1. And what you get is you can factorize the u to the alpha, and then you get 1 plus an error. Okay?
Divided by u to the alpha?
No, it is there. It's there. So everything you need to do is to ensure that this error goes to 0. Okay? You already know that, well, you know that this part goes to 0 when u goes to 0, but what you really need is that these coefficients go to 0 uniformly. Okay? So that would finish the proof. So that's a lemma. So with this, actually they go in probability. And it's uniformly in I. So with this, you simply have that this Laplace transform It's exactly what you want, plus a small error that goes to 0 with n. So the consequence when n goes to infinity is just converge to a stable random law. So let's go to the lemma. So let's look at these A, N, J. Okay. So as we are polymer people, we like to put a log in front of everything. So this is just log z n t minus 1 j minus the alpha norm of the same partition function. And then we could play the same game. So let's divide by the alpha norm of the partition function at one instant before. So what we end up with is this v bar at time t minus 1 minus something that I will write explicitly. Just dividing everything by this quantity at time t minus 2. Okay, so if we were in the stables case, we already knew that we would know that these things are stable random variables. So this is something we can control directly by some extreme techniques. But now, of course, we don't know that we are in the stable case. So what we will do is to take some information from the same computation, but we will try to be less well, let's say not extract information that precise as the convergence to the stable law. So as before, you could look at this thing here, condition now with respect to the history up to time t minus 2. And just bound this sum by this quantity. Okay, so that's quite brutal. It's less ambitious. So we have something like that. So now, of course, it's something, this error now does not depend on n, but the only thing we know is that it goes to 0 when u goes to 0. So we lose the dependence on n. But now we lose the dependence on n here, which means that we have somehow a uniform estimates on this Laplace transform, which means that we can use the Tauberian theorem uniformly for these guys. So by the Tauberian theorem, we get that the probability that the nt minus 1 j to be bigger or equal to x goes like a constant over x to the alpha. Okay? And now we can, now we are in good shape to get some kind of Poissonian convergence for these guys. So what we do, what we know is the following, is that if you properly renormalize these partition functions, now as they have these states and they are independent, you can use standard theorem for convergence to Poisson processes. So this will converge in law to a point process xj. Now j is bigger or equal to 1. And this is the description of this process explicit. It's a Poisson point process on R plus with an intensity proportional to 1 over x to the 1 plus alpha. Hence, it will have two properties that are relevant to us. So first, this density, this intensity is integrable. So the max over this point process is almost surely bounded. Okay, it has the rightmost point. And the second quantity, the second conclusion, sorry, is that the sum of the alpha powers of these Cj's is infinite. Okay? So we just go back to this expression. So we can bound log a and j just by the maximum over j from 1 to n of the zeta bar. Here I should use I divided by n to the 1 over alpha minus 1 over alpha log, and then I get the sum of the zeta bar divided by n to the alpha to the power alpha. Now, these things are converging to this Poisson point process. This converges to something which is bounded. This converges to this series which is divergent. So this whole thing goes to minus infinity. Well, from here, just divide by.
You forgot the log, or?
I forgot a log?
I don't know.
Yes, I forgot a log. Yes, sorry. Yes. Yes, so you have the log of the I in j goes to infinity uniformly in j, so that's exactly what you want. That finishes the proof.
Did you divide? Did you correct that?
Sorry?
You divided. Did you correct that? Or you didn't? Yeah.
Is it okay?
No.
Okay. Okay, so I can stop here.
Any questions?
So, in this perturbative case, you show that you have like almost random walk, I guess. With,
Well,
Okay.
You have this, that the Z bar has a stable law almost.
Right.
Do you have the same conclusion also for the speed Vn and sigma n squared?
We are not able to do that at the moment, but that's indeed a good question. Yeah, I don't know.
You do have independence, I think. So what goes wrong, I wonder?
Well, this jump upsilon n is no longer necessarily independent of. Well,
here you also use independence of the Z bar, and I thought that didn't depend on the.
No, I did not use independence. Yeah, I use independence, but on I, on the different sides. But what you need for the previous computation is independence in time, which I don't necessarily have if I'm not exactly in the Solomon model.
And you don't get enough control with this?
No. No, I don't. Yes?
I want to say, quantitative level, so you have very heavy tail, so the maximums so you have this matrix, and there are some very big numbers there.
Right.
Floating around. Right? On every row, there is one row, n to the alpha, I guess, and on every, and altogether, it will be n to the 2 alpha.
Okay.
And so this polymer chooses, so there is one strategy is just from I go to the big number corresponding to this I, then to big number corresponding to U1 and so on.
Okay.
Or you can just go choose the largest among this, but then you cannot connect to the largest on the next level. So you can go somewhere and then come to the largest. So how this polymer really behaving?
Oh,
How it's floating among these large numbers.
So that it really concentrate around this maximal trajectory.
Well, choose large. The best strategy for them is to just choose large values.
Right.
Of this omega, which are floating around.
Right.
And how is it done?
Yeah, I don't know actually, but there is a huge entropy, right? I mean, there are many, many paths. So
But entropy is huge.
yeah, but the
Totally
maximum.
huge. It is n to the alpha entries you get.
Yeah.
So you get huge entries.
Yeah.
You can probably compute frequency, how often the polymer visits sites with weights above a certain level.
Okay.
Perhaps there is a linear rate.
So how
Okay.
much does it differ from the just a random walk? Just constant weight?
Yeah. So the honest answer is that I don't know. As I said, the most precise information that we have is that about the stationary measure for the polymer measure, that we know it has atoms, but we don't have anything more precise than that. Okay, yeah, it's a good question, but I don't know.
I think you can look at it, you can study it.
Okay, yeah.
Okay. Any more questions? If not, let's answer.
Thank you.